Okay, folks, so our main goal in this section is to derive a formula for computing double integrals in polar coordinates, similar to what we did in the last section. And that will enable us to compute volumes over polar regions. But before we even do that, let's just make sure we all agree on what we're trying to find here. So let's go ahead and start off with our polar plane. So there's our polar plane. Careful, this isn't the XY plane. We're not in the rectangular coordinate system. We're in the polar coordinate system. So remember that our points, they live here. They look like maybe r comma theta. So what we'd like to do is we'd like to construct a multivariate function that's going to map from the polar coordinate system, which we could still think of as being r2, to r. But we're going to do it this way, by mapping some f of r comma theta to some z. So put it another way, you're going to input a radius and you're going to input a theta into some function, and it's going to output some height. Okay. Well, one way to envision that is to think of, we take our polar plane, and just like we did in the rectangular coordinate system, we imagine this third axis coming out of here. It's still the z-axis. And so, for example, if we plug in r comma theta into our function and it outputs some z, we could think of that as being the order triplet r comma theta comma z, and that gives us some point in this three-dimensional space here. R comma theta comma z. So there's that order. I may have said pair just a minute ago. I meant triplet. And so if we did that, oops, that was supposed to be green. If we did that for all points in the domain, that would give us some surface, and we can think of that surface as living above the polar coordinates. So just as we did before, we're going to take some region of the polar plane, and that region, I mean for it to look, so let's label it R, I mean for that region to look something like this region here, for what we'll be doing in our next class. And so each one of those points would get mapped up here somewhere into some ordered triplet. And then we're ready to talk about sort of an intuition for what we mean by volume. Then we can think of the volume of this that we're going to discuss in a double integral as being the volume formed by the shape where we've got this surface living above the polar plane here. And so the volume would be the shape between the polar plane and the surface. So that's our goal. Our goal, just like before, is we want this volume. Okay. So we're ready to give a name to it. I'll go ahead and give a name to it now. We're going to go ahead and say that the net volume, anyway. Remember, net volume allows for this plane to dip below the, in this case, the polar plane. So the net volume we're going to denote this way, or we're going to think of this way. It's going to be the double integral of r of f of r theta dA, just like it was before. But what's different here is, and you should be curious about, is what do we mean by this change in area? What does that mean in the polar coordinate system, not the rectangular coordinate system? Okay. So that's where we're going here. And by the way, let me just let the cat out of the bag. In class, we're going to develop the double integral for f of r theta dA, and we'll say that we can, similar to Fubini's theorem, we can evaluate this as an iterated integral from some theta equals alpha to some theta equals beta, from some r equals a to some r equals b, of our f of r theta, and then not quite what you would expect, or maybe, I don't know, maybe you do, the dA, the equivalent of the dA here is going to be r dr d theta. So all of this is going to take the place of our dA. And if I were you, I would be a little bit perplexed about that factor of r that shows up there. So that's where we're going to be really careful when we develop this in class. And it's going to be essential that we not lose that factor of r. Okay, so that's all I want to say about the double integral in this video. But what I want to do is I want to lay some groundwork for how we're going to derive this iterated integral in our next class. And so what I'd like to talk about is the area of a sector and the area of a rectangle in our polar coordinates. Okay. So first of all, when I say area of a rectangle, let me put the rectangle there in quotes, because I'm going to, in polar coordinates, I'm going to consider this shape right here in our polar coordinate system, we're going to consider it as a rectangle. Why are we thinking of this shape as a rectangle? Well, if you look at the way we've described this shape, it's a collection of ordered pairs, r comma theta, where our r value ranges between two values. R is ranging between a and b, and our theta value is ranging between two fixed values. This is very similar to what we did in the Cartesian coordinate system when we said we had a rectangle that would look like the collection of ordered pairs x comma y such that a was less than or equal to x, which was less than or equal to b, and c was less than or equal to y, which was less than or equal to d. Okay. So notice that this particular region that we've constructed here, and you've sketched some regions like this in the previous page, we consider this a rectangle as far as our polar coordinates are concerned. Okay. So you can see we've got this radius here, and remember radii in our polar coordinate system give us r values give us concentric rings, and so we've got this is our r equals a, and then for our r equals b we've got this circle, and then we're ranging from this theta right here, that's our theta equals a, theta equals alpha, all the way up to over here, this theta value, this is where theta is equal to beta, and that gives us this side. So this shape here has four sides, where the upper and lower side are given by the fixed radial values, and the left and right side are given by the fixed theta values. So we do want to think of this as the polar equivalent of a rectangle. Okay? So we're going to spend some time building the formula for the area of a rectangle in our next class. By rectangle, I mean polar rectangle. But let's go ahead, we're going to need as a prerequisite the area of a circle. So in the space remaining, I'm going to put a circle, and I use the aid of the machine for that. And I'd like to talk about what we mean by, well, what do we even mean by a sector of a circle, and then how do we find the area of such a sector. So here I've got a circle with radius r, and then let's go ahead and take the easiest sector we can for right now. Let's go ahead and just go up some angle theta, and we go ahead and give ourselves a new region bounded this way, and we can think of that as a slice of the circle, right? So we're going to call this geometric shape a sector. And how do we find the area of a sector? Well, maybe you remember the formula from geometry, but we're going to need this, and everything where this r shows up hinges on understanding the area of a sector. So let's go ahead and say, if you don't know the area of a sector, what we could do is we could say that the area of the sector of the circle should be in proportion to the area of the entire circle, as the angle of the sector, theta, is in proportion to the angle used in constructing the entire circle. So there's a proportion there. What angle is required to construct an entire circle? The answer is 2 pi. Well, we already know what the area of a circle is, so area of a sector, which I'll just abbreviate AS, is to pi r squared, the area of a circle, as the theta, the angle of the sector, is to the angle that constructed the entire circle. And now if we solve this proportion for the area of the sector, we would get, and rewriting it, let's write it as pi r squared theta all over 2 pi, and now notice the pi's cancel. We could simplify this then as 1/2 r squared theta. And so I want you to know that for next time, that the area of a sector is given by 1/2 r squared theta. So we'll need that for our in-class work next time. Okay. The other thing is I recommend that you begin memorizing this formula for computing volume in the polar coordinate system. So go ahead and get started on that, and we'll go ahead and put this integral to work in the next example.